Hi everyone, I'm Laurent Condat, a research scientist in the Visual Computing Center. This work in the context of optimization for machine learning has been presented at ICML last year. This is joint work with Peter Richterich and 3 students in his group. The setting is federated learning, a recently proposed paradigm in which a very large number of users participate in a global learning task in a collaborative way. Each user has a device like a phone or computer with data stored on it and communicating with a distant server or master, which is, for instance, some Google service in the cloud. But for privacy reasons, and because communication is typically slow and costly, the goal is to communicate as little as possible. So let us introduce operators TI, which model a set of computations done on each device. The goal is to find the global model X star, which is a fixed point of T, the average of all these operators TI. Most optimization algorithms can be formulated as iterative fixed point algorithms. But such algorithms also have a much broader range of applications beyond optimization. So here is the algorithm we proposed. At every iteration, the operators TI are applied on the current model in parallel at each device. And communication happens not after every iteration, but only once in a while, for instance, every 10 iterations. When communication occurs, the master receives all these local vectors, averages them, and broadcasts the updated version of the model. And the algorithm resumes at the next epoch. We could derive convergence results for this algorithm and other randomized versions. For instance, here, if all operators are contractive and the algorithm communicates every h iterations, it converges linearly to some model X dagger. And it does so h times faster than the standard algorithm communicating at every iteration. X dagger is not the same as X star, the ideal fixed points that we would like to estimate, but their distance can be characterized. So this is consistent with what we observe in practice, which is that the algorithm converges faster with respect to the number of communication rounds to an estimate of the solution up to a neighborhood of the solution. To sum up, we propose a rigorous analysis of this strategy, which consists in doing local computations and communicating once in a while. The method is able to estimate the solution of a learning problem, or more generally, a generic fixed point estimation problem, up to some accuracy with reduced total communication load. Thank you for your attention.